going to finish up this discussion, initial discussion about viscosity, but viscoelastic deformation is not a part of the homework. Viscosity is. Everything by the end of this lecture is, but not viscoelastic deformation. I'll talk about the exam at the end. So let's just remember what we were talking about and learn a little bit more about viscosity today. Well, I hope you remember that we talked about creep. If you have constant stress for a long time, then you are going to have deformation which increases with time. So to warm up for me to see that everyone still remembers something from Monday, let's first just look at this stress diagram. We have a stress versus time. What would be a strain versus time if this material was linear elastic? Just take 30 seconds and remind yourself what would be a strain versus time for this stress diagram if the material was linear elastic. I won't give them yet. It may be too late. Okay, let's not be distracted by caramel. Here, if we have constant stress applied over time, let's call this T0. What would be the strain time diagram if the material was linear elastic? Last time, I showed you that the strain time diagram for a linear elastic material would look something like this, because gamma is tau over g in a linear elastic material. So if there is no stress, if a stress is 0, a strain is 0. 0 divided by g is 0. If you apply a stress tau, you are going to get a strain, and let's see how much it would be. It would be tau over g, and as long as you are holding the stress, you are going to have this much elastic strain, and the moment you release the stress, the same moment a strain drops back to 0. This is linear elastic material. The deformation is instantaneous and it's fully recoverable. Now, if we would increase the loading duration, if you would hold it a little bit longer, the load. So instead of T0, you would apply T0, you would apply some, I use a T, the uppercase. What would happen? If you do that, only this would, in the beginning it would be 0, only this would last longer. So you're going to have a strain also for a longer period of time, because the strain is proportional to stress. And the moment you release it, you go back to 0. Everybody is with me? Now, if you have a viscous material, what happens? We learned about Newton and Newtonian fluids. In that case, you have the proportionality not between a stress and a strain, but between a stress and a strain rate. That's how fast the strain is changing with time. So if I want to write something here, I cannot write gamma is equal to tau over g as before. I can write d gamma dt. How fast the strain is changing with time would be equal to tau over mu. And what is this parameter? What did we call this? Viscosity. Viscous materials, viscosity. So, if the material is viscous like caramel, good example, and you apply load on it, and try not to increase your force. You just keep it like that for a long period of time. What happens? As you hold it longer, it's going to expand more and more. Do you agree? Even if when you don't change the stress, right? And if you stop, I'm not a very strong person. If you stop, does it go back to where it was? No. It stays exactly deformed as it was before. So actually asphalt behaves very much like caramel. So if you don't have any stress in the beginning, you start with 0 and the rate of change is 0. So if you start with nothing and nothing is going to change, there will be only nothing. Make sense? So in the beginning we have 0. But then the moment you apply stress, what does this mean? This is the slope of this line, gamma over time. The slope would be tau over viscosity, stress over viscosity. So you have a constant slope, and then when you reach to the point after T0, gamma, actually you can calculate it. It would be tau over mu times T0. And afterwards, when you stop the stress, I'm talking about the black loading. When you stop the stress, the rate of change will be 0. What does that mean? The rate of change would be 0. Nothing changes. So whatever I have stays the same. The slope is 0. If I would increase the duration, like in the red curve, if I continue pressing this with the same load, I'm not increasing the load. Of course, this is not very scientific, but I try not to. And I'm patient enough, so if you continue, what will happen? It continues to deform. And the moment you stop, it stays exactly the deform as it stops deforming. Just stays like that. You can eat it if you want now. So, the longer you wait, as you can see, the amount of strain is proportional to how long you hold the load. Yeah. So I hope you remember now what viscous materials are. So we need to learn a little bit more about them today. This we solved last time. For example, I told you that the linear elastic material, we use a spring to model, right? For a viscous material, we use a dashpot. A dashpot represents something like that, a piston inside a cylinder, and it represents resistance. The resistance which is proportional to the rate of application of the force. So if you pay attention to the door closers, they have something here which works a little bit like a dashboard. So that's why some of them work better. So it kind of closes the door slowly. Or if you have ever tried in the gym, the rowing machines. Anyone has tried? What happens if you pull it very fast? It's very hard, it becomes very hard. So the force, the resistance is proportional to the strain rate. If you do it very fast, it becomes very stiff. If you do it slowly, it is much easier, if you have ever tried it. Yeah. So anyway, so stress, because the stress is proportional to the rate of a strain in this case. This is normal stress. So far we were talking about shear stress. So in any case, we use a dashpot. We normally draw it like this to represent a viscous element. This is a model, viscous model. And you know how it behaves, the stress-strain behavior. Now, so far, we were using shear stress. Remember, it was always tau equal to mu d gamma over dt. But the same thing also applies to normal stress. The material is viscous. This is normal stress. I didn't apply any shear. It would be difficult. And the definitions, nothing changes. Instead of eta, we have here lambda, but this is still viscosity. And instead of gamma, we have epsilon, etc. Nothing changes in terms of what is going on. Any questions so far? So if we compare, for example, a high viscosity versus a low viscosity, and we look at a stress versus a strain rate, since the slope is viscosity, if the material has lower viscosity, the slope is smaller. If it has higher viscosity, the slope is larger. Now tell me, between, let's say, caramel and water, which one has higher viscosity? Caramel. Because viscosity is a measure of resistance to flow. So when we say the material has higher viscosity, it means that it resists the flow more. We'll talk about this a little bit more later. And if we compare the normal stress and versus shear stress, you see that the relationships are pretty similar. In both cases, the stress is proportional to the strain rate. In one case, it's normal stress, normal strain rate. The other case is shear stress, shear strain rate. In terms of the values, the two viscosities are a little bit different, but they are both viscosities. Depending on whether you have shear or normal, the value is different. So for normal stress, the viscosity is 3 times larger than the shear stress. And sometimes these are called dynamic viscosity. And in a nutshell, if you would compare linear elastic versus viscous materials, you can see in linear elastic, we have Hooke's law. In viscous materials, we have Newton's law. And in linear elastic, a stress is proportional to a strain. In viscous, a stress is proportional to a strain rate. So putting everything like that together. Any questions? No. And the units. Last time I told you that this parameter, whether you are talking about eta or lambda, the unit is Pascal second. This is sometimes called poise. And this comes from the name of a French physicist who contributed to viscosity. And the pronunciation, if I do this right, is Poiseuille. No, Poiseuille. I'm sorry, I practiced but in French it's a little bit more complicated. In any case, it's Pascal second, doesn't matter if you have eta or lambda. And higher viscosity means a slower or faster flow. Slower, exactly. Because remember that what we are characterizing with viscosity is resistance to flow. Now, if you compare different types of material, you see how the viscosity is different in terms of Pascal second or oil. And you will start with very low viscosity for fluids, and as you go towards solids, it becomes larger and larger. One important material with a very distinct viscoelastic behavior is, of course, asphalt. And you see that it's still much higher than some other, let's say, syrup or some other materials. So my question is, where do you think caramel falls? What do you think, how much would be the viscosity of caramel? Throw a number.
1,000.
1,000 is a good number. Any other ideas?
Wow. 3,000.
3,000? Much larger. It turns out that there are people who actually measure viscosity of caramel, and they don't do it just for fun. People who work in food industry, they have to measure the mechanical properties of caramel, for example, because viscosity is a property that controls how you like, for example, your chocolate or whatever sweets that are made from caramel. So you see that at 35 degrees, it's about 800. So in room temperature, maybe it's actually more in the thousands. But you also see something else. You see that as the temperature is increasing, what happens? So here in the x-axis, we have temperature. What happens? The viscosity is decreasing exponentially. And you may have noticed this or experienced this in your life before. If you forget this piece of caramel, and if by some miracle the weather becomes nice and tomorrow is sunny and hot, what will happen? What will happen with the caramel in your bag? It melts, the start to flow, you would not even recognize it after a while. So temperature generally causes the viscosity to decrease, and you can easily imagine. And this is not only for caramel. All materials, if you look at the dependency of viscosity and temperature, you see that as you increase the temperature, the viscosity goes down. And this becomes very important, for example, when you design asphalt concrete pavement. Because if you work in a very hot climate, and you have to choose the right material, otherwise in summer, your pavement starts to slow. Or the pavement becomes very soft. You can imagine. It is just like that. In hot temperatures, it becomes very soft, and then it cannot carry the load of the trucks. You may have seen if you travel to some parts of the country where the weather is a little bit warmer than here, you can see some, at the truck wheel path, you see some sort of, you have noticed, this is called rutting. And it happens when, for example, asphalt was not yet designed. It just performs in summer under the load. So this is important. We'll get back to that when we discuss asphalt. But there is even analytical expressions which relates the viscosity to temperature. And you can see that this relationship is exponential and includes the notion of activation energy. So this is a material science class, so you need to understand a little bit how the temperature makes the material, for example, less viscous. What happens? First, a quick review, what is activation energy? Activation energy, as you can see, if you want to go from state A to B, in chemistry you have seen that it's the amount of energy that you need to start this reaction. And if you use a catalyst, you need less activation energy, for example, as you can see. But if you don't remember chemistry much, try to think about it as like a small thing that you have to go over for going from one state to the other. How does this relate to temperature and viscosity? It turns out that in order to make a material flow, you have to apply, for example, shear stress. You have to break some bonds so that it can flow easily, right? And if you apply temperature, if you apply heat, this heat provides some energy, and you have more activation energy to provide basically the work necessary to break these bonds. So it is easier for the material to flow. And if it is easier to flow, you have less viscosity. Any question about that? So remember that viscosity decreases with temperature. The material flows easier because as the temperature goes up, we have more energy to break the bond and make the material flow. There is another quantity very related, and this is called kinematic viscosity. It's nothing else but viscosity divided by density. Just that you are following and you don't fall asleep, try to calculate what would be the unit of kinematic viscosity. This is more like a definition that comes up from time to time. So the unit of dynamic viscosity or viscosity that we have talked so far is Pascal second. If you divide it by density, what would it be? One more example. That's mass density. It's a good exercise. Remember what density is, what viscosity is, how to divide things. So density is and Pascal if you substitute, you should get how many have that? Meter squared over second. This is the unit. Pascal and kilogram are related. Okay. Now, so far, we talked about Newtonian fluids, where stress was proportional to a strain rate, and we call this proportionality, we call this viscosity. Now, there are the real materials that we work with, they're not that simple. So the stress versus the strain rate may look like, for example, this kind of reddish curve. No, it's more like purple. So in this case, you see as you increase the strain rate, if I draw a small tangent to the curve and I calculate eta, the eta becomes smaller and smaller. The slope becomes smaller and smaller. So this is a behavior which is called shear thinning. This is common, for example, to concrete, fresh concrete has this kind of behavior. So as you can see here, eta, this is eta, is not constant. As you go from beginning to the end, it becomes smaller. It means that as you increase the strain rate, if you apply the force faster, the material becomes less resistant. It resists less. This is the behavior. There are, on the other side, materials which have the opposite behavior. If you apply the strain faster and faster, they become more resistant. And one important material here, not to civil engineers, but let's say to army, is body armor materials. This is what we want, right? That if something comes at a very high strain rate, that you have a very high resistance. You don't want the material starts to flow. There is another class of important non-Newtonian fluids which behaves like this. If you apply the stress very, very slowly, when the rate is almost zero, it behaves like linear elastic material. It yields up to the yield. So we don't start from zero. We start from yield stress. And once it starts to yield, it behaves like a Newtonian fluid. Toothpaste behaves like that. So when you press, and at some point when you press hard, then it starts to flow. It's coming out of the tube. But that's not very important to our applications. What is important is the steel behaves like this. Once it is behaving plastically, it behaves like a Newtonian fluid. So before you have yield, and then you have Newtonian fluid. And basically the next slide summarizes what I just told you. So if you want to write it, you have here the yield stress, and afterwards it just looks like Newtonian fluids. This is sometimes, these are called Bingham fluids. It's named after a scientist. So this is something you have to be familiar with. Any questions so far? So far we learned about viscosity, fluids, dynamics, kinematics, that Newtonian fluids are not the only ones. Now is the time to also learn how to measure viscosity. rheometer. That's the generic name of like an instrument that is used to measure viscosity. There are different types of this kind of instruments. One is the one we see here. You have coaxial cylinders. This one is fixed. The other one is rotating at a certain strain rate. You fill the material here, and you measure how much stress is exerted on the tube which is fixed. So you get a point on the stress-strain rate diagram. You change the rate, you get another point. You change the rate, you measure stress, you get another point. You fit a line, you look at the slope, and that gives you viscosity. Now, different materials, of course, will have different slopes. So if you want to look at, let's say, water, glass, molten glass, and oil, you can very easily see which one will be which. So the one with the highest viscosity would be molten glass, right? Oil would be the second one, and water would come here. The way to measure it is really changing the strain rate, measure the stress, you have points, and then you fit a line, you look at the slope, and this gives you the viscosity. There is another kind of rheometer where you place the material between two plates. You always have to exert some strain rate, and you have to also measure stress. In this case, you have two plates. The one on the top is rotating. You measure the torque that we're applying to keep a certain strain rate. The one at the bottom is fixed. And here you fill the material. Again, you have an Excel sheet probably. You measure the torque, you calculate the stress, you know what is the strain rate, and you do it for different strain rates. You pick a line, and the slope would be viscosity. To see how it looks like, for example here, soil specimen. So basically you have this apparatus, this is the top plate which is actually rotating. You place the specimen, and this one rotates, and here you measure the torque and you measure the strain rate. This is how it works. I don't know if they show you this in C337. No? Haven't seen it. It's a little bit more complicated test, so maybe that's why. It turns out that you can even measure viscosity in the field. For example, you can have this kind of plates that you can bring and place inside fresh concrete. And again, what you measure is how much torque you are applying. You also measure the strain, and you always have to look at the relationship between a stress and a strain rate. This is more like an introduction. I don't expect you to know the details, just that you have an idea how to measure it. Now, we didn't have any quiz or homework on this topic, so it's important to look at least one example here. So here we have a linear elastic element, that's the spring, and a dashpot, which is the viscous element, and they are in series. Everyone knows when I say they are in series what that means. It means that the total strain is equal to the strain of dashpot plus the strain of the spring. Now the question is, if I apply a constant stress, which one of the diagrams in the next slide is the response? Try to talk to your friends, and when you find the answer for the other diagrams, you may want to draw the model. And I need to see the correct solution. The answer is D. But it's important to reason things also. So the model looks like something like that. Yeah. These are in series, so you can say that the epsilon is equal to epsilon due to a spring and the epsilon due to dashpot. This one is instantaneous and it recovers. So when you apply the load, what happens is this is due to a spring, and then afterwards you are going to have with a constant slope of sigma over lambda in this case, you are going to have strain because of the dashpot. Now the moment you release the load, what recovers is exactly the amount which was due to the spring elongation. So these two will be completely equal. And the rest stays there. Always think about the caramel. If you press it, it doesn't go back. It just stays the same way. And because of that, this is the correct answer. So next week, you are going to learn much more complicated model, where we like Lego, like Lego, you put different elements together and you make much more complicated models. Now, we have a few minutes to talk a little